The university's role in the project includes developing a prototype insulation material using wheat straw, doing some demonstration work with the 3 prototype materials developed by the project, leading the life cycle assessment work of the project, and finally in dissemination activities for the project. We identified wheat straw as our preferred material following extensive experience over the last 10 or so years working with that as a potential insulation material in construction. It's an abundant material, it's a co-product of food production. Like other bio-based building materials, in the growth of the plant, then it uses up atmospheric carbon dioxide and effectively stores or banks it within the product. Wheat straw, as well as being an affordable, sustainable biomaterial, then it also has some very favourable characteristics as an insulation material. Good insulation qualities, but also it's a hygroscopic building material. This means it responds to moisture levels around it, and that gives it favourable characteristics in terms of helping to regulate heat flow and moisture flow through the building fabric. Straw bales have been used in construction for around 100 years. And at the moment people are using essentially agricultural bales that have been made by farmers for storage. Whilst these have good use in construction, there are limitations in terms of their wider adoption because of their size. So what we are trying to do is re-bale straw to make it more widely suitable for construction and a wider use of applications as an insulation material. The research work that we're undertaking as part of the project is seeking to address the potential barriers to wider adoption of this material. So we're characterising the material to understand its thermal performance and also its fire resistance and other important issues that potential users will ask about. So barriers at this stage, of course, are, well, the next stage is in terms of upscaling production and making a sustainable larger supply chain, and in that process the final costs of production are going to influence that. The raw material in itself is very cheap, and I anticipate that the final costs of production will also be very competitive compared with other insulation materials. Providing high-level quality insulation to our buildings is important to delivering energy-efficient buildings. So insulation materials will remain important to the construction industry. At the moment, existing mainstream construction materials largely rely on fossil fuels and high-energy production methods. So finding alternative insulation materials with a much more favourable environmental impact has to be better for delivery of lower carbon, and more energy efficient buildings. I think the opportunities for benefits to the Interreg region from this project stem from upscaling of the prototypes that are being developed and job creation and new construction products. I think so there are wider benefits to the construction industry, and there are wider societal benefits from having energy efficient, healthy houses for people to live in.
So the initial testing after we've produced a bale, there are a few different characterization tests that we go through. The first one being a mechanical test. We'll use the machine that's behind me in order to compress it at a rate of about 10% of its total dimension per minute. This is basically just to make sure that once you have the insulation within a wall, that its own self-weight doesn't compress and you're not left with air gaps. So once we've done that, we've done the compression test, those bales can then be set aside, and then we will move upstairs and use our small environmental lab where we'll look at thermal conductivity. This is done with a variety of machines, and ideally, the most common one is a guarded hot plate, where we'll have a differential of about 20 C, and it takes anywhere from 1 to 3 days to reach steady state, and that'll basically give us a U value on a small contained environment through a single sample. Those panels will then be placed into a large controlled environmental chamber, which will then be monitored for long periods of time for a series of 2 consecutive tests. The first being a steady state, where we're just looking at determining a U value. You know, what is the amount of energy passing through the panel. The second series of tests, where we'll start introducing moisture, we'll raise the humidity on one side, again representative of the outside of a wall or outside of a home, and we'll then measure the moisture transport through that wall, and more importantly then the moisture transport as it leaves that wall. We want to see how fast it's going to have a moisture uptake, but also how fast the moisture is going to leave the panel as well. And all of those in turn will take about 6 weeks of long-term monitoring.